December 7, 1936. Bridgeport, Connecticut. The machine tool industry had reached a unanimous verdict. American manufacturing needed $7,000 specialized machines to compete with European precision. Single-purpose equipment, maximum rigidity. One machine, one job. Through the cold Connecticut air, steam rose from factory smokestacks where established wisdom ruled every serious machine shop. European-trained engineers had proven their point for decades. Universal machines were toys, not tools. Too light for heavy cuts. No precision. No future. Then Rudolf Banno sat in his delivery truck outside a customer's plant, grabbed a paper bag from his lunch, and sketched something that would make every expert wrong. A vertical spindle on a ram that could swivel and extend. A turret design allowing infinite positioning, all mounted on a single, solid cast iron frame. The sketch looked impossible to manufacturing veterans who knew better. How could one small machine replace 3 or 4 specialized tools? 800 miles from European workshops, the most decisive challenge to manufacturing wisdom was taking shape. Not in superior complexity, not in premium price tags, but in elegant simplicity that would outlast everything the experts said was necessary. The morning of January 15, 1937, brought bitter Connecticut cold that made metal ring like bells when struck. Inside the cramped workshop on Iranistan Avenue, Rudolf Banno studied his paper bag sketch for the 100th time, knowing that transforming those hurried lines into functioning metal would require choices that could make or break everything. While Kearney and Trecker welded massive steel frames in Milwaukee and Cincinnati Milling Machine Company assembled their proven horizontal mills from rolled steel plates, Banno made his first critical decision. Gray cast iron. Not the cheaper, faster steel that every competitor used, but the material that would absorb vibration like a sponge soaks water. Cast iron cost more. Took longer to machine. Required foundry work that steel fabrication avoided. But Banno had felt the difference in his hands. Steel frames transmitted every cutting force through the machine like a tuning fork, while cast iron dampened vibrations before they could destroy precision. The foundry pattern consumed 6 weeks. Banno carved and shaped every detail himself, ensuring the internal ribbing would provide maximum rigidity without unnecessary weight. When the first casting emerged from the furnace in March, it weighed 875 pounds, solid, dense, purposeful. The competition's steel frames might look more modern, but this gray iron base would outlast them all. Then came the surfaces. Every machine tool manufacturer faced the same challenge: how to create perfectly flat, perfectly straight ways that would guide moving parts with thousandths of an inch precision. The industry standard solution involved steel shims, thin metal strips inserted between components to adjust alignment. Quick, cheap, effective for initial setup. But shims shifted over time, requiring constant readjustment and eventual replacement. Banno rejected shims entirely. Every surface that touched another surface would be hand-scraped by skilled craftsmen using techniques that dated back centuries. The process was brutal and expensive. A master scraper would coat a precision straight edge with Prussian blue dye, drag it across the cast iron surface, then examine where the dye transferred. High spots received attention with a curved scraping tool, removing metal flake by microscopic flake. The scraper would check, scrape, check again, scrape again, for hours or even days until the surface met specifications. Magnus Wahlstrom watched the first scraping operation with growing concern about labor costs. Each way required 40 to 60 hours of handwork. Skilled scrapers commanded top wages. The process couldn't be rushed or automated. But when Banno demonstrated the results, surfaces so perfectly mated that a thin film of oil created an airtight seal, Wahlstrom understood they were building something different from everything else in the market. The spindle presented another crucial decision point. European mills typically mounted horizontal spindles in elaborate gear trains that provided dozens of speed options but required complex maintenance. American manufacturers like Brown and Sharp built sophisticated vertical spindle heads with intricate speed change mechanisms that impressed customers but multiplied potential failure points. Banno's design eliminated complexity wherever possible. A A single-speed spindle motor drove the cutting tool directly through a simple belt system. No gear trains, no multiple speeds, no elaborate transmissions, just consistent, reliable power delivery that any mechanic could maintain. Critics would later call this approach crude, but simplicity meant reliability, and reliability meant profit for shop owners who needed machines that ran every day. The ram and turret combination represented Banno's most innovative breakthrough. Traditional mills required operators to manually position workpieces for different cutting angles, a time-consuming process that often required multiple setups for complex parts. The Bridgeport design allowed the spindle head itself to swivel and extend, bringing the cutting tool to any position around the workpiece. One setup could handle operations that required 3 or 4 different machines in conventional shops, but the innovation that would prove most crucial was nearly invisible to casual observers. The one-shot lubrication system consisted of a single lever connected to a precision pump that delivered exactly the right amount of oil to every bearing, weigh, and sliding surface simultaneously. One pump stroke lubricated the entire machine. No forgotten grease fittings, no dry bearings wearing prematurely, no maintenance schedules that demanded constant attention. By late summer, the first prototype was taking shape in the Iranistan Avenue shop. The gray cast iron base sat solid and immovable. Hand-scraped ways guided the table and knee with glass-smooth precision. The ram extended and retracted without the slightest binding. The turret swiveled through its full range with mechanical certainty. Every component fit together with the precision of a fine watch, yet the overall design maintained elegant simplicity. The first test cuts revealed the machine's character. Where European mills impressed with their elaborate controls and German machines demonstrated their superior metallurgy, the Bridgeport simply worked. Feed the spindle into the metal. Watch perfect chips curl away from the cutter. Measure the finished surface with precision gauges. Repeat. Hour after hour, day after day, the machine delivered consistent results without drama or complications. But would the market accept it? Machine shop owners had been trained to expect complexity as proof of capability. The Bridgeport looked almost primitive compared to the elaborate European imports with their dozens of levers, multiple gear trains, and sophisticated control systems. Could a machine this simple command respect in an industry that equated complexity with quality? The final assembly of serial number 1 took place in early August 1938. Banno personally adjusted every component, ensuring that decades of planning and months of careful construction had produced exactly what his paper bag sketch had envisioned. The machine was ready. The question remained whether American manufacturing was ready for it. August 8, 1938. The freight truck rumbled through Syracuse, New York, carrying serial number 1 toward its first real test. Precision Castings Corporation had agreed to try Banno's machine based on reputation alone. They knew his milling heads, trusted his craftsmanship, but had never seen anything like the complete mill now secured in the truck bed. Plant foreman Joe McCarthy watched the delivery with skepticism that turned to curiosity as riggers unloaded the gray cast iron machine. It looked substantial despite its compact size, purposeful in ways that impressed men who worked with metal every day. Within hours of installation, reports began filtering back to Bridgeport that defied every prediction. The little mill was outperforming machines 3 times its size and 10 times its price. McCarthy called personally to report that his operators were completing complex setups in minutes instead of hours. The ram and turret combination allowed them to machine intricate parts without repositioning the workpiece, eliminating the multiple setups that consumed so much production time on conventional equipment. More importantly, the machine delivered precision that matched the best European mills. Test cuts held tolerances of 0.02 of an inch consistently, part after part, shift after shift. The hand-scraped ways maintained their accuracy under heavy cutting loads. The gray cast iron base absorbed vibrations that would have destroyed precision on lighter machines. But perhaps most shocking to McCarthy and his crew was the machine's reliability. Day after day, the Bridgeport simply worked without the temperamental behavior they expected from complex equipment. Word spread through manufacturing circles with the speed that good news travels in tight-knit industries. By October, Banno was fielding inquiries from shops across New England. The price point of $995 made the decision easy for small job shops that could never afford multiple specialized machines. They could buy a Bridgeport for less than they spent on maintenance contracts for their existing equipment. Orders began arriving faster than the small Iranistan Avenue shop could handle. Banno hired additional scrapers and machinists, but the hand-fitting process couldn't be rushed. Each machine required the same careful attention to surface preparation and component alignment that made the first mill successful. By early 1939, the backlog extended 3 months. Wallstrom urged expansion, but Banno insisted on maintaining quality standards even as demand exploded. The economic pressure of recession-era manufacturing worked in Bridgeport's favor. Shop owners who had postponed equipment purchases for years found themselves forced to buy something, and the Bridgeport offered capabilities they couldn't get elsewhere at any price. A single mill could handle milling, drilling, boring, and light surface grinding operations that previously required 4 separate machines. The versatility meant smaller shops could compete for complex jobs they'd never been able to accept, but success brought scrutiny from established manufacturers who watched their market share erode to this upstart Connecticut company. Trade journals published analytical articles questioning whether universal machines could deliver the precision that specialized equipment guaranteed. Technical experts pointed out the obvious limitations: fewer spindle speeds than German machines, lighter construction than British mills, simpler controls than Swiss equipment. The criticism stung, but orders kept flowing from shops that cared more about productivity than technical opinions. By 1940, Banno needed serious manufacturing space. The company moved to a larger facility on Barnum Avenue, installing proper foundry equipment and expanding the machine shop to handle increased production. The price held steady at $995 as volume manufacturing brought down unit costs. More importantly, field reports continued validating the design's fundamental soundness. Mills shipped in 1938 were still running perfectly, requiring minimal maintenance beyond routine. Lubrication. Then came December 7, 1941. Pearl Harbor transformed American manufacturing overnight from peacetime flexibility to wartime urgency. The War Production Board surveyed available machine tool capacity and discovered a critical shortage. Major manufacturers like Cincinnati, Kearney, and Trecker, and Brown and Sharp were already committed to specialized wartime production. Thousands of small job shops needed equipment to handle constantly changing military contracts, and they needed it immediately. The Bridgeport mill proved ideal for wartime conditions. Its versatility allowed shops to switch rapidly between different military components as contracts changed. Aircraft parts, torpedo components, tank elements, artillery shells, the ram and turret design handled them all without lengthy retooling. More crucially, the simple, robust construction meant the machines kept running under the demanding schedules that wartime production required. Military inspectors who initially questioned whether a $995 machine could meet defense standards quickly became converts when they saw the results. Precision remained consistent even under heavy use. Reliability exceeded that of much more expensive alternatives. The hand-scraped ways and gray cast iron construction delivered the accuracy that military specifications demanded while maintaining the productivity that wartime schedules required. Production exploded during the war years. The Barnum Avenue factory added 2,400 square feet in 1941, then another 4,200 square feet in 1944. Employment grew from 12 workers to over 60 as demand far exceeded capacity. The 5,000th mill shipped in January 1945, representing a production rate that would have been impossible with the complex, time-consuming manufacturing processes that European competitors used. By war's end, Bridgeport mills were machining components for every major weapon system in the American arsenal. The machines that critics had dismissed as inadequate for precision work were producing parts that determined whether bombers reached their targets, whether ships survived enemy attacks, whether tanks performed reliably in combat. The ultimate validation came not from technical journals or industry experts, but from the performance of American military equipment that depended on parts machined on Banno's simple, elegant mills. The 10,000th machine rolled off the Barnum Avenue production line in 1948, marking a decade of continuous success that had transformed a paper bag sketch into an industrial phenomenon that was reshaping American manufacturing one shop at a time. The peacetime economy of 1946 brought challenges that wartime urgency had masked. European machine tool manufacturers, their factories rebuilt with Marshall Plan funding, launched a sophisticated campaign to reclaim American markets. Swiss mills arrived with precision spindle speeds that exceeded anything American manufacturers offered. German horizontal machines featured complex gear trains that provided dozens of cutting options. British vertical mills incorporated advanced automation that reduced operator skill requirements. Technical journals that had grudgingly praised Bridgeport's wartime contributions now published detailed comparisons that highlighted every limitation of Banno's design. American Machinist ran a devastating analysis titled Postwar Precision Demands that questioned whether simple universal machines could meet the sophisticated requirements of modern manufacturing. The article praised European engineering sophistication while describing the Bridgeport as adequate for simple work, but lacking the precision and sophistication expected in advanced manufacturing operations. The criticism stung because it contained elements of truth. Bridgeport mills operated at fixed spindle speeds, while German machines offered infinitely variable control. The simple belt drive system couldn't match the torque multiplication that elaborate gear trains provided. The manual controls required skilled operators, while European machines incorporated automatic feed systems that reduced labor requirements. In laboratory conditions, using ideal materials and perfect setups, the European machines often outperformed their American counterparts. Sales momentum slowed noticeably through 1947 and 1948. Customers who had bought Bridgeports during the war began considering European alternatives as their shops expanded. The price advantage that had driven early adoption seemed less compelling when sophisticated buyers could afford premium equipment. Machine tool distributors pushed European lines that offered higher profit margins and impressed customers with their complexity and advanced features. Internal pressure mounted within the Bridgeport organization. Engineering staff, led by newly hired designers with formal training, pushed hard for modernization. They proposed adding variable speed controls, automatic feed systems, and electronic positioning aids that would match European capabilities. Marketing personnel demanded features that could compete directly with Swiss precision and German sophistication. The arguments were compelling: evolve or become obsolete. Banno faced the classic innovator's dilemma that had destroyed countless successful companies. His simple, elegant design had conquered the market through reliability and versatility, but competitors were winning customers with superior specifications and impressive demonstrations. The board of directors questioned whether the original concept had reached its natural limits. Perhaps the time had come to abandon simplicity for the complexity that customers seemed to demand. The financial pressure was undeniable. 1948 sales growth stalled completely, while European competitors gained market share each quarter. Major accounts that had relied on Bridgeport equipment during the war were placing orders with Deckel, Hauser, and other European manufacturers whose machines featured specifications that made the American mills look primitive by comparison. Stock prices reflected investor concerns about the company's long-term viability in increasingly sophisticated markets. But instead of following conventional wisdom, Banno made a decision that shocked his engineering staff and mystified industry observers. Rather than adding complexity to match European competitors, he doubled down on the fundamentals that had made his original design successful. He studied field reports from customers who had operated Bridgeport mills for a decade, comparing their experiences with shops that had invested in more sophisticated alternatives. The pattern that emerged contradicted everything the technical journals claimed. Bridgeport mills were still running perfectly after 10 years of continuous operation, while many European machines had required major overhauls or complete replacement. The hand-scraped ways maintained their precision longer than any shimmed alternative. The simple belt drive systems needed only routine maintenance, while complex gear trains demanded expensive specialist attention when they failed. More revealing was the cost analysis. European machines might deliver superior laboratory performance, but their total cost of ownership often exceeded a new Bridgeport's purchase price. Sophisticated control systems required specialized technicians for repairs. Complex automatic systems broke down regularly, causing production delays that eliminated any efficiency advantages. The Swiss precision that impressed buyers in showrooms became expensive maintenance headaches in actual production environments. Banno's response to the competitive pressure was characteristically counterintuitive. Instead of adding features, he invested in better materials and more precise manufacturing. The price increased to $1,115 in 1950, but every dollar went into improvements that enhanced durability rather than complexity. Castings received additional stress relieving. Scraping operations extended to include surfaces that had previously been machined. Component tolerances tightened to levels that exceeded most European standards. The R8 spindle taper, introduced in 1952, exemplified Banno's approach to innovation. Where European manufacturers developed complex quick-change systems with multiple moving parts and precise adjustments, the R8 used a simple tapered design that locked cutting tools with mechanical certainty. No complex mechanisms, no adjustment procedures, no specialty tools required. Just a taper that gripped with increasing force as cutting loads increased, then released instantly when the drawbar loosened. The design became an immediate industry standard that competitors rushed to copy. Its elegant simplicity accomplished everything that complex European systems achieved, while eliminating the failure points that caused expensive downtime. Decades later, the R8 taper would still be the preferred standard for countless machine tools, proof that superior engineering doesn't require complicated solutions. Field reports through the 1950s validated Banno's strategy completely. While European competitors introduced new models every few years to address problems with previous designs, Bridgeport mills continued running reliably year after year. The machines that critics called crude were outlasting everything the sophisticated Europeans could build, proving that American manufacturing wisdom valued different priorities than European engineering theory. By 1960, the market had delivered its verdict decisively. A Bridgeport mill sat in nearly every American machine shop and vocational school. The design that technical experts had dismissed as obsolete had become the foundation of American manufacturing education and the backbone of the job shop industry that drove economic prosperity across the country. The economic boom of the 1950s created the perfect laboratory to test competing manufacturing philosophies. American industry expanded at unprecedented rates, driving demand for machine tools that could handle both high-volume production and flexible job shop work. European manufacturers seized the opportunity, flooding American markets with sophisticated equipment that promised to revolutionize manufacturing efficiency through advanced automation and precision engineering. Deckel Universal mills from Germany featured elaborate indexing systems and dozens of spindle speeds. Swiss Aciera machines incorporated precision groundways and complex gear trains that delivered laboratory-grade accuracy. British Herbert Mills offered advanced automatic feed systems that reduced operator involvement to simple push-button control. Each European machine came with thick technical manuals, specialized tooling, and claims of superiority over crude American alternatives. The initial results seemed to validate European superiority. New installations impressed plant managers with their sophisticated controls and precise performance specifications. Trade publications featured glowing reviews of European engineering advancement. Industry conferences showcased complex machines that demonstrated capabilities far beyond anything simple American mills could achieve. The technical advantage appeared overwhelming and decisive, but reality and production environments told a different story that emerged gradually through the decade. The complex European machines that performed flawlessly in controlled demonstrations began showing their limitations under the demanding conditions of actual manufacturing. Automatic feed systems jammed when cutting irregular materials. Precision ground. Ways required frequent adjustment to maintain accuracy. Elaborate gear trains needed specialized maintenance that few American shops could provide effectively. More critically, the sophisticated control systems that impressed buyers became expensive nightmares when they malfunctioned. European manufacturers built their machines with precision components that required expert attention when problems developed. Replacement parts often took months to arrive from overseas suppliers. Specialized technicians commanded premium wages and weren't always available when urgent repairs were needed. Production delays from equipment failures frequently exceeded any efficiency gains the advanced systems provided. Meanwhile, Bridgeport mills from the 1940s continued running reliably in shops across America. The hand-scraped ways maintained their accuracy despite years of heavy use. The simple belt drive systems needed only routine belt replacement and basic lubrication. When problems did occur, any competent machinist could diagnose and repair them using standard tools and readily available parts. The machines that critics had dismissed as obsolete were proving their worth through consistent, dependable performance. The contrast became particularly evident during the recession of 1958, when manufacturing budgets tightened and every maintenance dollar counted. European machines that had impressed with their sophisticated capabilities suddenly became expensive liabilities. Complex systems required constant attention from specialists whose wages exceeded the productive value they provided. Replacement components cost more than entire Bridgeport mills. Downtime from sophisticated equipment failures often paralyzed production for days or weeks. Shop owners who had invested heavily in European equipment began questioning their decisions as repair costs mounted. A typical Swiss mill required annual maintenance contracts that exceeded $5,000, while Bridgeport mills needed only basic lubrication and occasional belt replacement. German horizontal machines demanded specialized tooling that cost more than most shops' entire cutting tool inventory. The total cost of ownership that seemed reasonable during prosperous times became prohibitive when economic conditions tightened. But the most revealing comparison emerged from productivity studies that measured actual output rather than theoretical capabilities. European machines might cut metal faster under ideal conditions, but their sophisticated systems required lengthy setup procedures that consumed productive time. Automatic controls that promised to reduce operator skill actually increased complexity, requiring extensive training that most shops couldn't afford. The precision that looked impressive in laboratory demonstrations often proved irrelevant for typical job shop work that rarely demanded tolerances tighter than Bridgeport mills could easily achieve. By the early 1960s, the market was delivering a clear verdict through purchasing decisions that contradicted technical opinions. New Bridgeport orders continued growing while European manufacturers struggled with declining sales and expensive warranty claims. Major corporations that had experimented with sophisticated foreign equipment quietly returned to American suppliers whose machines required less maintenance and provided more reliable service. The 100,000th Bridgeport mill rolled off the production line in 1967, marking a milestone that no European competitor would ever match. The simple design that engineering experts had criticized as inadequate had become the backbone of American manufacturing, installed in virtually every machine shop and vocational school across the country. The machine sketched on a paper bag 30 years earlier had outlasted generations of supposedly superior alternatives. More significantly, the Bridgeport design remained essentially unchanged from Banno's original concept, while European competitors introduced new models every few years to address problems with previous versions. The hand-scraped ways, gray cast iron construction, and simple mechanical systems that critics had dismissed as old-fashioned proved to be fundamentally superior to complex alternatives that looked more advanced but performed less reliably under real-world conditions. Educational institutions provided the ultimate validation of American manufacturing philosophy. Vocational schools and community colleges across the country standardized on Bridgeport mills for training the next generation of machinists. Students learned fundamental machining principles on equipment that would serve them throughout their careers, regardless of what sophisticated systems their employers might install. The skills developed on simple, reliable machines transferred directly to more complex equipment, while students trained on specialized systems often struggled with basic mechanical understanding. By 1970, industry observers recognized that the Bridgeport phenomenon represented something more significant than successful product design. It demonstrated that American manufacturing philosophy valued different priorities than European engineering tradition. Where European designers pursued theoretical perfection through sophisticated complexity, American innovators sought practical solutions through elegant simplicity. The market had decisively validated the American approach, proving that machines which simply worked reliably outperformed equipment that impressed with advanced specifications, but failed when dependability mattered most. The design that began with a paper bag sketch had evolved into an industrial standard that defined American manufacturing capability, proving that sometimes the best engineering solution is the one that keeps working when everything else breaks down. The 1980s brought a technological revolution that promised to transform manufacturing forever. Computer numerical control systems emerged from aerospace and defense applications, offering precision and automation that dwarfed anything mechanical systems could achieve. CNC mills could execute complex programs automatically, maintaining tolerances of tenths of thousandths while operators monitored multiple machines simultaneously. The future had arrived, and it rendered manual machines obsolete, or so the experts proclaimed. Major manufacturers rushed to develop CNC versions of their traditional equipment. Bridgeport itself introduced computer-controlled mills that featured sophisticated programming capabilities and advanced servo motor systems. Trade shows showcased gleaming white machines with digital displays and push-button controls that impressed visitors with their space-age appearance. Manufacturing consultants advised companies that manual machines would become museum pieces within a decade. The initial CNC installations delivered everything promised and more. Programmed operations ran with mechanical precision that eliminated human error. Complex parts that required hours of manual setup could be machined automatically once programs were developed. Production rates increased dramatically for high-volume work, where programming costs could be amortized across thousands of identical parts. The technology represented a genuine advance in manufacturing capability, but beneath the impressive demonstrations, fundamental problems emerged that paralleled the European machine experience 30 years earlier. CNC systems required specialized programming knowledge that most shop personnel didn't possess. The computers that controlled these machines used proprietary software that only trained technicians could modify or repair. When electronic components failed, entire production lines stopped until specialists could diagnose and fix problems that might involve circuit boards costing thousands of dollars. More troubling was the planned obsolescence built into electronic systems. Computer technology evolved rapidly through the 1980s and 90s, making control systems obsolete within 5 to 10 years. Manufacturers discontinued software support for older machines, leaving owners with equipment that couldn't be programmed or repaired. Circuit boards failed and couldn't be replaced. Memory systems became incompatible with updated software. Perfectly functional mechanical components became scrap when their electronic brains died. The contrast with mechanical Bridgeport mills became stark as decades passed. Machines from the 1940s, 50s, and 60s continued operating reliably in shops across America. Their mechanical control systems never became obsolete because they didn't depend on rapidly evolving technology. Any competent machinist could operate them effectively without specialized computer training. Repairs required mechanical skills that were widely available rather than electronic expertise that few possessed. Financial reality made the comparison even more dramatic. CNC machines typically cost 10 to 20 times more than equivalent manual mills, but their useful life expectancy was significantly shorter. Depreciation schedules assumed 7 to 10 years of service before technological obsolescence made replacement necessary. Even when mechanical components remained sound, electronic systems failed in ways that made repairs uneconomical compared to purchasing newer equipment. Meanwhile, vintage Bridgeport mills retained their value in used equipment markets because they remained fully functional regardless of their age. A 1950 mill could perform the same operations as a brand new manual machine, limited only by normal wear rather than technological obsolescence. The hand-scraped ways that had seemed old-fashioned compared to CNC precision actually lasted longer than electronic systems that initially appeared far superior. The economic cycle of CNC replacement became predictable and expensive. Companies invested heavily in sophisticated equipment, trained operators in programming and operation, then faced complete obsolescence when control systems became unsupported. Each replacement cycle required new training, new programming, and new maintenance procedures as manufacturers introduced incompatible systems that couldn't use previous investments in tooling or programs. Job shops faced particularly difficult choices because their diverse, low-volume work didn't justify complex programming for simple operations. CNC machines that excelled at repetitive production often sat idle or operated inefficiently on one-off jobs that manual mills handled quickly and economically. The flexibility that had made Bridgeport mills successful in job shop environments became even more valuable as manufacturing became increasingly specialized and automated. By the 2000s, a remarkable pattern emerged in American machine shops. Many successful operations ran mixed fleets that included both modern CNC equipment and vintage manual mills. The computerized machines handled high-volume, repetitive work where programming costs could be justified, while the mechanical mills took care of prototype development, repair work, and custom jobs that required human judgment rather than automated precision. The most telling evidence appeared in equipment auctions where failed businesses liquidated their assets. Modern CNC machines often sold for scrap value because their obsolete control systems made them unusable, while decades-old Bridgeport mills commanded premium prices from buyers who recognized their continuing value. The machines that critics had dismissed as primitive outlasted generations of supposedly superior replacements. Educational institutions provided another validation of mechanical machine tool value. Technical schools and community colleges continued teaching fundamental machining skills on manual equipment because students needed to understand basic principles before advancing to computer-controlled systems. The tactile feedback and direct mechanical connection between operator and cutting tool couldn't be replicated in computerized environments where programmers worked remotely from actual machining operations. More importantly, employers consistently preferred machinists who had learned on manual equipment because they understood what was actually happening during cutting operations. CNC operators who lacked manual machining experience often struggled when programs didn't work as expected or when unusual materials required adjustments that weren't covered in standard procedures. The fundamental skills developed on simple mechanical machines proved essential even in highly automated manufacturing environments. The ultimate irony became apparent as the 21st century progressed. While CNC technology advanced rapidly, creating ever more sophisticated and expensive systems, the basic mechanical principles that made Bridgeport mills successful remained unchanged. Metal still needed to be cut by sharp tools applied with appropriate force and speed. Precision still depended on rigid machine construction and accurate guidance systems. Reliability still required simple, maintainable mechanical designs rather than complex electronic systems prone to obsolescence. 86 years after Rudolph Banno sketched his idea on a paper bag, original Bridgeport mills continued earning money in American machine shops, while countless generations of more advanced replacements had been discarded as technological orphans. The design that began with elegant simplicity had proven more durable than any sophisticated alternative that followed.